I'm an unusual astronomer in that I don't actually know how to use a telescope. I don't know any of the constellations, so I actually do more of the math and physics side of things. So I try to model and interpret the observations and predict the observations, and that'll come into the story a little bit later. So what I want to tell you about today is really, in some sense, a detective mystery. It's about how we figured out the last part of our understanding of where in the universe everything we find here on Earth actually comes from. Where was it produced? So I want to take you back to high school chemistry. I don't know about you, even though I'm a scientist, I actually really didn't like chemistry and didn't do very well in it. I was much more interested in the abstract stuff in physics. But in chemistry, what we've learned is that essentially everything here on Earth, our biology, metabolism, eating, breathing, drinking, the beer that you have consumed tonight, how your body reacts to that, right? All of that has to do with just a few basic building blocks which are encapsulated in the periodic table of elements. So these are ordered from simple things like hydrogen, which is just a proton and an electron, to more complicated things like berkelium or californium, which have huge numbers of protons, huge numbers of neutrons, and huge numbers of electrons. And one of the amazing discoveries in astronomy and physics is that we've actually figured out, for the most part, not entirely, but for the most part, we figured out where all of this is actually produced. It wasn't here at the beginning. Most of these elements have been produced in specific places in the universe and then got incorporated into the sun and the Earth and the solar system when it formed 4.5 billion years ago. And very briefly, that story is that the lightest elements, hydrogen, helium, lithium, were produced in the first 3 minutes of our current understanding of the history of the universe, so back at what we call the beginning and the Big Bang. And everything else heavier, the oxygen that we breathe, the iron in our blood, the carbon in our bones, and as we'll see, the gold on many of our fingers is all produced by nuclear processes, fusion processes, and related processes in stars like the sun or in more dramatic things like stellar explosions. And this story's really been worked out over the last 70 years. We've been able to isolate where each of these different elements in the periodic table was produced. But there's been a gap in that understanding. And the gap in our understanding has actually been a pretty big gap. It's been about half of the heaviest elements in the periodic table, things like platinum, berkelium, californium, unanillium, your favorites like that, uranium, gold. Those elements, we've not really understood where in nature those were produced. And amazingly, figuring that out required building an entirely new type of telescope that looked at the universe in an entirely new way. And this is the story about seeing the universe not with light, which is what our eye sees, or radio waves that you hear, or gamma rays or X-rays that are used to take a picture of your broken bone or your skull. Those are all forms of light. Instead, unraveling this last mystery about the origin of the elements required a telescope that detected what are called gravitational waves. So these are waves that have nothing to do with light, but instead have to do with gravity. And I think one way to think about this is that these are waves that communicate to everything around how gravity is changing. So gravity is the force that holds us here on the surface of the Earth, that holds the Earth in the orbit around the sun. And if you have a situation like this, where two objects are going around each other, how does some distant person or some distant alien far away from these two planets or these two stars spiraling around each other, how do they know that the two objects are moving around and they're not just sitting there? And the answer is that there's a wave that's communicated out into space that carries the information that gravity is changing, that the two objects aren't just sitting there, they're actually undergoing this beautiful dance around each other. And that wave is sort of illustrated schematically there, okay, as this Ripley pattern where this is intended to kind of convey the idea that the strength of gravity is subtly changing in time and space due to the dance of these two objects around each other. And these waves are a prediction, actually, of Einstein's theory of gravity, his theory that's called general relativity. They were predicted in 1916. It's actually a great story in the history of physics. It took people 40 or 50 years to decide that they were real waves, real things that could exist, and not just weird mathematical artifacts. The theory of general relativity is really, really complicated math. It confused even the best physicists at the time, and it took a while to work out that they were real things that could hopefully actually someday be detected. And indeed, about a century after Einstein's theory of gravity, these waves were ultimately detected. So if you want to see a source in the universe that's emitting these waves of changing gravity, what you want is objects that have very strong gravitational pulls. Okay, gravity is strong, and where the objects are moving quickly around each other so that gravity is changing rapidly in time. That's how you get a strong source of these waves of changing gravity. So what we need to look to in the universe is the strongest sources of gravity that we know of anywhere in the universe. And that is not objects that we're actually familiar with here in the solar system. That's not stars and planets. It's more exotic types of objects, black holes, which, as we know from science fiction, are really goddamn scary. And neutron stars, which are still sort of stars, but they're really weird stars. They're stars that have masses similar to our sun, but sizes similar to a city, so similar to the size of San Francisco. So the sun is 100 times larger in radius, 300,000 times larger in mass than the Earth. So imagine all of that shrunk down into a region no bigger than a city, and that's what a neutron star is. And as its name suggests, it's made mostly of neutrons. So those other things that are in the nuclei of atoms, neutrons and protons make up the nucleus of atoms. Neutron stars are made mostly, but not entirely, of neutrons. And black holes are made of, well, we don't really know what they're made of, but they're basically just made of gravity. They're objects where gravity is won out over everything. All of the mass in the object has collapsed down to a point, and it's really just essentially a ball of energy and gravity that is, in fact, the strongest sources of gravity that we know of in the universe. So these two objects, essentially because they're the smallest things we know of, where you have a lot of mass in a really small region, they are the strongest sources of gravity that we know of in the universe. So then the way you get a strong source of gravitational waves is you need two of these objects with really strong gravity to be moving around each other in one of these dances, so gravity is changing in time. And that's what's illustrated. This is actually now a computer simulation that solves Einstein's theory of relativity on a computer, and it predicts what would happen if you have two black holes spiraling around each other. As time goes on, the two black holes actually get closer and closer. And again, the yellow and blue is intended to convey that as the objects get closer to each other, gravity gets stronger, right? Gravity is stronger for Mercury. The gravity of the sun is stronger for Mercury than it is for the Earth. And so as time goes on in the movie, the two black holes get closer and closer, gravity gets stronger and stronger, and the strength of gravitational waves gets bigger. And that's what's illustrated here. As time goes on, the pattern goes up in amplitude. That's stronger gravitational waves because the two things are closer to each other. And the other thing you'll notice is that the peaks and troughs get closer to each other. And that's reflecting the fact that as the two black holes get close to each other, the time it takes them to orbit around gets shorter, right? Mercury goes around the sun in 88 days. We go around the sun in 365 days. Jupiter, further away, goes around in 12 years. So that kind of condensation, the fact that the pattern gets shorter and shorter, is just the fact that when objects are closer together, they orbit each other more quickly. So that's the kind of thing we'd like to see actually out in the universe a source of gravitational waves. Two black holes, two neutron stars, a neutron star and a black hole, something like that orbiting very close to each other, spiraling in, producing this huge burst of energy in the form of these waves that transmit out into space that gravity has been changing during that collision. This may not look like a telescope. Okay, but this actually is the telescope that detected these gravitational waves. This is called the LIGO telescope. LIGO stands for Laser Interferometer Gravitational Wave Observatory. So just to remind you, I don't actually do experiments, I don't observe things, I predict things, and I do the math to interpret things. So honestly, in detail, I really have no idea how this telescope works. It's astonishing to me that it actually works. This is an extremely difficult measurement, what they've done. But the basic idea is the following. There's a mirror here, and there's a mirror there. And there's a mirror there and a mirror there. And there's light bouncing back and forth between those mirrors. And as one of these waves comes by, what it does is it very subtly alters the distance between the mirrors. And you can measure accurately the distance between the mirrors by studying the properties of the light that's bouncing back and forth between those mirrors. Okay. This measurement, just to give you a sense of how hard this is, the closest star to us, does anybody know what the closest star to us is? Okay, what's the second closest star? Damn you. The Proxima Centauri system, it's actually 3 stars orbiting around each other. It has planets, maybe it has aliens, but okay. That's a few light years away. This measurement measures the distance between these mirrors that's equivalent to measuring the distance to the Proxima Centauri system to an accuracy of about the width of a human hair. They measure the distance between the mirrors more accurately than the size of a proton. It's just an extraordinarily difficult experiment. It's amazing that it actually works, but it does. It took a while. The first ideas for how to do this were in the 1970s. They built the initial telescopes in the late 1990s. They're very, very patient. They observed for like 15 years and saw absolutely nothing, right? Which for me, I have ADHD, that would not be possible. I would get bored, but they were patient. They kept making the telescope better and better and better. And eventually in 2015, they finally detected for the first time, at least on this planet, they detected a source out in the universe that had produced gravitational waves. And what they detected was the collision of 2 black holes. This is sort of an artist's conception of what that collision might look like, spiraling in, spiraling in. 2 black holes collide. What you're left with at the end is 1 black hole. Okay? And this shows the actual data from the telescopes. There's actually 2 of these telescopes, and the reason there are 2 is because if you only have one, what you would mostly detect is trucks going by or somebody dropping their cell phone like 100 feet away from the instrument, which causes the ground to shake a little bit, and that's what they would detect. So you build 2 of them, in this case, one in the state of Louisiana, one in the state of Washington, so you know you're actually looking at a source out in the universe and not a truck going by. And what you see in this pattern is exactly what I showed you in that computer simulation. The signal gets stronger, the pattern gets shorter in time as the orbit happens faster and faster, and then once you're left with a new black hole sitting on its own, having just collided and formed, then eventually the signal dies away. Okay. So there's an amazing amount of interesting science that's come out of this. This is the best confirmation that black holes exist as predicted by Einstein's theory of relativity. It's our best tests that Einstein's theory of relativity is actually the right theory of gravity. Lots of beautiful stuff that's come out of this. But what I want to do is skip forward to August of last year, when after having detected 5 of these colliding black holes, LIGO finally detected the collision of 2 neutron stars. And there was a tremendous amount of excitement and hope and anticipation in the community, at least the nerdy physics community, for the detection of 2 neutron stars. because neutron stars are made of matter. It's weird. It's mostly neutrons. It's not like stuff we're used to in the periodic table, but at least it's matter. Black holes are really just gravity, just energy. And so there's no way we know of to see colliding black holes other than through these gravitational waves. The collision of two black holes does not, we think, produce any light. But colliding neutron stars, which involve normal matter, can produce some light. And so the hope was that what would happen is when LIGO detected two colliding neutron stars, that there would be at the same place and the same time on the sky, a new source of light on the sky. And that's exactly what was detected. Thank you. Again, I didn't actually do any of the observations. So this is the galaxy outside of which the two neutron stars collided. That is a source of light that appeared about a day after the gravitational wave collisions. And then about 2 weeks later, that source of light was gone. This is a picture taken with a telescope that sees light that's a little bit longer wavelength than your eye can see, called infrared wavelengths. But in fact, basically every telescope on the Earth and every telescope in space that could try to look at this did try to look at it. 70 observatories on every continent. Yes, there are telescopes in Antarctica. It's actually a good place to do astronomy. It's very dry. That may sound counterintuitive, but it's cold enough that it's actually quite dry, so it's a good place to do astronomy. So every telescope, Hawaii, South America, Africa, Australia, looked at this event. Something like a third of the world's astronomers are on papers observing this event. That's 3,000 or so astronomers. That's probably roughly like a tenth of the data scientists in San Francisco. A bunch of things in space, and we've learned a tremendous amount, and I'm really only going to tell you one part of the story of what we've learned from this event, which is the story that's related to the origin of the elements. So what we think happened is that during the collision of these two neutron stars, most of the matter that was in the neutron stars ended up collapsing to form a black hole that was left behind after the collision. But a little bit of material was actually flung out into space during the collision. And that's illustrated in a sort of animation here done by my colleague Dan Kaysen at Berkeley, which shows this sort of cloud of debris spreading out into space. Now, what happens if you take mostly neutrons and a little bit of protons and you fling it out into space, what it turns out to do is it fuses to form heavier elements. But it doesn't make things like hydrogen, because you can't make hydrogen out of mostly neutrons, because hydrogen is just a proton. Instead, what you make is the elements in the periodic table that have more neutrons than protons. And those are exactly those very heavy elements in the periodic table: gold, uranium, Berkeley, Californium, unanillium, etc. Those are the elements that you produce if you fling out neutron star debris into space. And that neutron star debris is initially radioactive. It's really like a fission reactor. And so it produces a source of light that goes up and then fades away in time because it's kept hot by radioactive heating of this kind of cloud of radioactive waste that's flung out into space. And so we can interpret the light that was observed coincident with these colliding neutron stars and infer from that light some of what was actually produced in that collision, in that debris that was flung out into space. So we can use the details of this light to figure out that there was actually gold, platinum, berkelium, californium, and uranium produced, and not hydrogen, helium, carbon, and things like that. And so this event, this one colliding neutron star, produced something like 100 times the mass of the Earth of gold and platinum. So imagine if you could go mine that, right? That would be an extraordinary source of money. It's quite far away. It's going to take us a long time to get there. In addition, this is actually the only place in nature that we know, other than laboratories on Earth, where some very exotic elements that we in California, and particularly in Berkeley, like, called berkelium and californium, were produced. So something like a mass of the moon worth of berkelium and californium were produced in this collision, flung out into space, and are now happily drifting out there in space, having now cooled off to the point where we can't see that radioactive debris cloud anymore. So I've highlighted this discovery as sort of an experimental achievement, which it absolutely is, but I'd like to also highlight the fact that in this particular case, and this is actually how science often works, actually the theoretical predictions of what a cloud of expanding neutron star debris would look like were made in 2010 at UC Berkeley. This was my grad student, Brian Metzger, who Jeff Silverman, who's in the audience, was a grad student with at the time. We were calculating for a variety of reasons. We wanted to know, just because it seemed like an interesting thing to figure out, what would happen if you had a cloud of radioactive debris from neutron star mergers flying out into space. What would it look like? And so this line here is the theoretical predictions that we made in this 2010 paper. And the blue points are the actual detections of this particular event. And so this is a case where the theoretical predictions actually led the experimental discoveries and enabled a much richer and more detailed, more nuanced understanding of the observations when they actually came in. In many cases, the experiments lead the theory, but in this case, the theory actually led the experiment. So I just want to end. So Bart stole my thunder by quoting Carl Sagan. So I want to end just by kind of putting this result in context. So what does this teach us? So there's a couple of things I think this teaches us. So Sagan did indeed famously say that we are all star stuff. One of my colleagues puts it another way, that we're basically all nuclear waste. We are the byproducts of fusion processes that have happened in stars. So processes in stars and stellar explosions build up the heavy elements, the oxygen, the iron, the gold, etc. It's then flung out into space through a variety of processes. That material is collected into gas clouds, and planets and stars form out of those gas clouds. And what we've learned now, rather remarkably, is that literally all of our cells have a very small amount of gold. Okay? So in addition to maybe the golds in your jewelry, each of our cells has something like 1/3 of a milligram of gold, and that gold was actually produced in colliding neutron stars in the distant past, before the solar system formed, 5 billion years ago, 6 billion years ago, 7 billion years ago. 2 neutron stars collided, flung out into space this debris cloud that eventually got incorporated into the solar system and is now present in our bodies. In addition, I think perhaps even more remarkably, it turns out that uranium, also produced in colliding neutron stars, is actually important for the existence of life on Earth. So the uranium in the interior of the Earth decays. It's radioactive with a half-life of billions of years. It decays and it heats the interior of the Earth, and that keeps the interior of the Earth actually boiling. And that boiling motion in the mantle of the Earth is what is responsible for plate tectonics. Plate tectonics produces bad things like earthquakes, okay? But it produces good things like volcanoes. And volcanoes are important because they're the way that carbon dioxide and other gases get out into the Earth's atmosphere. If you didn't have volcanoes, all of the CO2 in the Earth's atmosphere would rain out, okay? Would go into rain and get incorporated into rocks, and there would be no ability to have photosynthesis, and so life on the Earth would die. And so we owe the existence of life in a very real sense on Earth today, or at least life as we know it, to colliding neutron stars 5 billion years ago. So thanks very much.
Go to nerdnite.com to find a Nerd Nite event near you. And don't forget to subscribe to our channel for our latest presentation.